Application systems are based on robust and reliable low-pressure technology, and accordingly represent a stage of successful progress in our efforts to apply fine spray technology to fixed extinguishing systems. The results speak for themselves. After a lengthy series of tests, there is scarcely any doubt that this system exploits all the major extinguishing effects of finely sprayed water to the optimum degree: the cooling effect and the suffocating effect. The intensive cooling effect is attributable to the high heat absorption capacity of the very large surface area of water produced by atomization. This effect is reinforced when the water fog evaporates, withdrawing even more thermal energy from the fire. On exposure to fire, the water evaporates to steam with a volume of steam to water of about 1600 to 1. Provided that a sufficient amount of water is finely atomized and accurately aimed into a fire, releasing large quantities of heat, the result is a blanket of steam over the immediate area of the fire that cuts off oxygen to it and produces a suffocating effect. Having said this, it must be added that using the most finely atomized water spray will never produce the same suffocating effect as CO2 or argon. The cooling and suffocating effects can only develop fully if the fine droplets of water are sprayed directly into the fire. When the mobile high-pressure extinguisher HDL-250 is used, this is no problem, as the lance attachment enables the water fog to be accurately aimed into the heart of the fire. Fixed systems are a different matter. If the extinguishing nozzles are too far away from the fire, or the water droplets too small, the water fog is deflected, as shown here, by convection currents. The extinguishing nozzles must be capable of forcing the droplets through the convection currents onto the fire. That is, they must produce fine droplets with high kinetic energy. Under realistic test fire conditions, it was soon apparent that hollow cone, that is, open swirl-type nozzles, which are frequently used, are less suitable, as they do not cover the central zone directly in front of the nozzle. In the twin fluid type of nozzle, nitrogen or air is used to atomize the water more evenly, but these systems involve elaborate installation measures and higher cost of components. In the final analysis, pulse nozzles have shown themselves to be the optimum solution. Their full cone spray pattern covers the entire zone in front of the nozzle, and they produce very fine droplets with high kinetic energy. This enables the spray to penetrate convection currents and reach the fire itself. A further major advantage of pulse nozzles is that their large, free cross-section makes them very much less accessible to blockage. An additional advantage is that adjustable spray angles, water throughput, and throw permit optimum alignment of the pulse nozzles with the protected object. All in all, an ideal basis for reliable protection with the mini-fog extinguishing system. This is demonstrated by an example of local application on gas turbines. A highly effective protection concept was developed in the course of lengthy trials with a 1-to-1 scale model. The pulse nozzles, which produced the best results in these trials too, are precisely configured to fit the protected object. Another reason for paying special attention to this concept is that its specifications are based on factory mutual draft guidelines. This series of trials shows just how effective extinguishing with a fine spray of water can be. This flaming spray of diesel fuel was extinguished in only 3 seconds because the water droplets were injected accurately into the fire. The great heat of the fire makes evaporation of the droplets so intense that the suffocation effect comes into play. In the interest of also finding out where the limits of fine spray technology lie, this trial apparatus was also fitted with obstacles to the spray of the sort that can occur in real-life installations. Obviously, when the spray is obstructed, the time required to extinguish the fire will be longer. Unlike inert gas, water fog does not work around corners. In this trial, the obstructions were too great, and the fire could only be controlled. Trials involving pool fires in various places in the apparatus produced similar results. This almost completely exposed pool fire of diesel fuel measuring about 1 square meter was extinguished in only 20 seconds after a pre-burning time of half a minute. In the case of pool fires too, obstructions to the spray lengthen the time required for extinguishing. It is all the more important to use suitable extinguishing nozzles and configure them so that the entire object is evenly blanketed with a dense fog of water. Although admixture of a foaming agent to form a surface foam will appreciably shorten the extinguishing time in the case of pool fires, this will not work around corners. Inert gas extinguishing systems are a different matter. Extinguishing gases such as CO2 or argon will get around any obstruction and permeate any cavity. The trials also confirm that a fine spray of water will extinguish big fires appreciably faster than small ones. The greater the amount of heat released, the more intensive the suffocation effect is.